Hello, this is chapter 15, looking at just a few tidying up for line 3. So I'm on slide 22. If you look, we're titrating a weak acid, a bunch of weak acids with a strong base, zero point 0.1 molarity of NaOH. And what's going to happen is, notice that it doesn't matter the strength of the acid that we're titrating. So as we're adding NaOH to, let's say, the first Ka versus here the top Ka, they all have the same equivalence point. It's still going to take 50 mils. So it's when we look at the actual reaction, what we have is whatever weak acid is dissociating. It has A minus. We're starting to add OH minus, and it takes the HA and converts it to A minus. So say we have an OH 50 mils, 0.1 molarity. That's going to give us right 0.05 liters multiplied by 0.1 molarity. And what we have is then 0.005 moles. It doesn't matter if we have a strong acid, weak acid. It's still going to, the OH is still going to be attacking the HA in the 1-to-1. And so it's still going to need 0.005 moles to react with the OH. So because it's 1-to-1, and of course, every time an OH reacts with an HA, it takes away the H and makes it A minus. So then what is the difference when we titrate a weak acid versus a stronger acid, all these Kas? All that's going to happen is as the acid weakens that we're titrating with the strong base, we're just going to start at a higher pH. So eventually, we start at this last one. Yeah, it's going to dissociate. It's going to create a slight buffer, and then it's going to have a change in pH. The very top one really doesn't show a great change in pH. It's already pretty basic, or it started off neutral. But the other Ks have just an equivalence point with a big pH change, and then of course it becomes basic at the end. It still takes the same amount of base to react with all of these different acids, and the only difference is the pH at the equivalence point. So the pH is going to be higher for the weaker acids. It's going to be lower for the stronger acids. All right, so, and of course then the half equivalence point is still going to be half of the 50 mils. So the 25 mils, which is half the equivalence point, you're going to get the pH equals pKa, and notice that the pHs are changing because the pKa's are changing. It's the different acids. All right. Here's the question for the last one. Why can't we find the pK for a very strong, of an unknown for a very strong acid? So if we look at, let's take the last one. It's a pretty strong acid. It starts at 1 maybe pH. Notice that it still kind of looks like a titration curve, right? It has this, looks like, well, it definitely has the equivalence point, and then we could just say, hey, here's the half equivalence point. But remember, we're not seeing it jump at the very beginning, so that's a good sign that that's a good sign that it is a strong acid. We don't see it, a little bit of dissociation and then creating a buffer over here. It's just basically a horizontal line, and then bam, the pH changes. And the reason for that, of course, is if we're titrating a strong acid with our really strong base, we're going to get the water and then the salt, which is completely neutral. And so every time we add the OH into HCl, it's just completely dissociating. It's completely reacting with the H, and the Cl is doing nothing. There is no buffer resistance with a Cl minus in the solution. All right, so hopefully that explains line 3, which was slide 22. Okay, thank you.